So J.D. Brown, who seems to me to be a quantum field theorist or string theorist, asks two questions. One, whether constructive field theory could be useful in establishing whether the two-dimensional or three-dimensional quantum field theories could be used in help constructing string or membrane theory. And the answer to that, I think, is that it's not really needed, since at least in two dimensions, the two-dimensional field theories we use to understand the nature of perturbative string theory, the worldsheet theories we use to describe the perturbative expansions of string scattering amplitudes, are largely based on soluble two-dimensional field theories, ones which are much simpler than the general class of that constructive field theory sometimes can prove exist but can't solve. What we really need to formulate those perturbative rules in string theory are soluble two-dimensional field theories. As far as three-dimensional field theories go, that might describe membranes, and people have been trying for decades to construct, to solve in order to have a description of what's called M-theory, in which the basic objects are not strings but membranes. So far, that's eluded our understanding completely. It's hard to imagine that the old-fashioned constructive field theory methods will prove useful, since those have had a lot of problems dealing with theories with extra symmetry, even gauge theories, and the kinds of supersymmetric three-dimensional field theories one would need to describe membranes wouldn't really fit into the kind of theories that constructive field theory have been useful for. As far as four dimensions go, J.D. Brown asks whether it is possible that four-dimensional quantum field theory doesn't exist, and that four-dimensional Yang-Mills is an approximation to the fields living on the worldsheet of a fundamental theory in lower dimensions. Well, first of all, four-dimensional quantum field theory, we believe, does exist. There's no rigorous mathematical proof of that, but the theories we use in the standard model, and certainly, especially QCD, which is a asymptotically free theory, surely do exist. Physicists are totally convinced of that. And in fact, a supersymmetric version of QCD, which is finite and conformally invariant, not only exists, but we now suspect is soluble, at least in the limit of large n, large number of colors, and may even have already been solved. So I don't think we need to resort to the imaginative idea that Brown suggests for describing consistently four-dimensional gauge theories.